Yesterday we talked about chemical reactions that occur in a single step, and then we could use uh, coefficients in the balance formula for our exponents. But let's go back and talk more about reactions that occur in a sequence of steps. And what we've learned is that if a chemical reaction proceeds in a sequence of steps, the rate law is determined from the slowest step because it has the lowest rate. So even though we have written one we think might be for the overall, technically what we have written is just for the slowest step. And this slowest step in a chemical reaction is called the rate determining step for that chemical reaction. So the overall rate of the chemical reaction is actually determined by this slowest step. Uh, and you probably have watched something similar to that. Here's an analogy, like if you've ever been in a buffet line and there are certain stations along the way that take longer for uh, you to choose your food or prepare your food, and the people kind of back up behind them. Well, the how fast you go through the line is often determined by that slowest place in the buffet. So let's look at this reaction where we have nitrogen dioxide reacting with carbon monoxide and to produce nitrogen monoxide and carbon dioxide. Now, this reaction is believed to be a two-step process, and it follows this mechanism right here. First of all, we have two nitrogen dioxide molecules will collide with each other, and as a result of this collision, one of the nitrogen dioxides gains an oxygen from the other nitrogen dioxide, and so it's now NO3, becomes nitrogen trioxide, and the other one that lost an oxygen is now going to be nitrogen monoxide. And this step that we've determined, or through experimentation, actually occurs slowly. The second step is where the nitrogen trioxide, this intermediate, reacts with the carbon monoxide to finally form nitrogen dioxide and carbon dioxide. And that step apparently takes place rapidly. Now, obviously, you'd have to design an experiment where you could do each of these kind of isolated from each other. Like this, the second step might be a reaction in which we've taken nitrogen trioxide and carbon monoxide and get them to react and find out what the rate that they occur at, but then we can see what the overall reaction is. Uh, Now, that first step is the slower of the two and is therefore the rate determining step. So when we write a rate law for the reaction that we have here at the top, we're actually writing the uh, the rate law just for this first step because it is the one that determines the actual rate. So the rate law would be just R equals K, and then we're taking two nitrogen dioxides and reacting with each other, so it takes two of them. So we could have written in step one just two N. Now let's take a look at sample problem D. Nitrogen dioxide will react with fluorine, and in the gaseous phase, remember this is a homogeneous reaction, and this is the balance equation. We have two nitrogen dioxide molecules reacting with one molecule of fluorine to form two molecules of what's called nitrile fluoride. And the proposed mechanism for this reaction is like this. One nitrogen dioxide molecule collides with the fluoride or fluorine molecule, and in the process, one molecule of nitrile fluoride is produced. Notice that the fluorine molecule has split and one fluorine stayed with the nitrogen dioxide to form the nitrile fluoride, and then we have one fluorine atom by itself. And then in the next step, we have that single fluorine atom reacting with the nitrogen dioxide. It doesn't need to be split, so we can kind of see maybe why it goes faster, but then it'll form a second molecule of nitrile fluoride. So what we need to do with this chemical reaction is to identify the rate determining step and then write an acceptable rate law. So if you look at what's given here in step 1 and step 2, we know that the rate determiner is the slowest step. So the rate determining step is step 1. So here are the two steps, and as we look at this, we can see that we have some intermediate structures that can be canceled out. The two fluorine atoms can cancel out, and then when I add them together, I'm going to have two, on the left side, I'm going to have two molecules of nitrogen dioxide plus the fluorine molecule, forming two nitrile fluoride molecules. So the intermediates F were canceled out, so those were intermediates. It's a something that was formed in one step that's used up in the next step. That's why it's called an intermediate. And we can write the law for this. The slowest one is just step 1, and it's just NO2 and F2. And there is no data that we can put exponents to it. So that is going to be our rate law there. R equals K times the nitrogen dioxide concentration times the fluorine molecule concentration. Now let's do sample problem E. This is a reaction involving reactants X and Y. They aren't saying what they are, but they're X and Y, and it was found to occur in a single step. This is a one step, so remember what we learned yesterday about one step. So here we have this reaction here is X plus 2Y forms XY squared. So X is reacting with Y, and then we're forming a larger molecule called XY. I said square, but it should be subscript 2. So it would be X di Y, whatever you want to call it. Okay, so we're going to write the law for this reaction and then determine the effect of each of the following on the reaction rate. Okay, since this is a single step, remember coefficients become our exponents. So we're going to have R equals K, or here's the questions that they want us to doubling it X, doubling Y, and using 1/3 of the concentration of Y. Okay, so but we still need to get our rate law. And because the equation represents a single step, the rate law is going to be written with where we're going to use the coefficients as our exponents. And the rate will vary directly with the concentration of X, which has an implied coefficient of 1. And then the rate of the other variable, Y, varies directly with the square of Y, which has a coefficient of 2. Okay, so we now have our exponents, so we're going to have R equals K times X, and then if you look in the first one here, we had a 1 right here, coefficient of 1. So right here is an understood 1 at that spot right there. And then for the y, we had a coefficient of 2. So we are going to have an exponent of 2 here. So this is our rate law right here. R equals K times X times Y squared. Okay, so now taking that rate law, let's answer the 3 questions that they want us to solve. So let's look at the rate law first. Okay, we have R equals K, and then it says we're doubling the concentration of X. So in place of X, we're going to write 2X. And then nothing's changed in Y, so we're just going to leave it the same. So it'll be Y squared. Now look at the first reaction law, rate law at the top. We had R equals KXY squared. Just remember the KXY squared. Okay, now if you look at the second one here, this part right here is going to become 2KXY squared. This was just KXY squared. This is 2KXY squared. So that means the rate over here is going to be 2 times this. So doubling the concentration of X is going to double the rate. Okay, it's going to double the rate because this 2 right here is 2KXY squared. Okay, now let's look at the next one. Okay, what if we double the concentration of Y? Okay, so in place of Y, we're going to put 2Y. Okay, we're going to put 2Y. But it's squared right here, right after it. So I'm going to take 2y squared. I'm going to get 4y squared times k and x. So now this becomes 4kxy squared, 4kxy squared. And compared to this one, that's 4 times as much as this. So in this one, doubling the concentration of y, this y right here, will increase the rate by 4. This will be 4 times as much. So the rate is now 4 times faster by doubling the concentration of y. Okay, now let's do the last one yet. In this one, we're going to change only y, but we're going to make y 1/3 as much as it was before. 1/3. So we're going to put in here 1/3 y. Or if you like it in math, that's y over 3, if you like that. But 1/3 y would probably work better in this situation. And then we're going to square it. So when you square 1/3, that's the same thing as taking 1/3 times 1/3. And if you remember from math in fractions, this is going to be 1/9. 1/9. So now I have 1/9 kxy squared. The rate now is 1/9 what it was before. 1/9 what it was before. Because y has been squared down here.